In this video, I will explain the proof of Theorem 2.18 from the lecture notes. Namely that, given a measure space for an infinite monotonic sequence of measurable sets, the measure satisfies the corresponding sigma continuity property. First, let us briefly recall what a measure, a measurable space, and a measure space are. According to definition 2.15 from the lecture notes, a measure is a non-negative and sigma additive function where sigma additive means that a mu on sigma algebra A on omega with possible values of plus infinity for any countable, which again means any finite or countably infinite sequence of sets from a sigma algebra that are pairwise disjoint. So the intersection of any two different sets from the sigma algebra is the empty set. Furthermore, the image of the empty set is equal to 0. Next, the sets A1, A2, etc., which are elements of the sigma algebra, are called measurable with respect to sigma algebra, and the ordered pair of omega and A is a measurable space. Finally, the ordered triple of omega, the sigma algebra A, and mu is called a measure space. Now let us recall the characteristics of a measure space. For a given measure space, omega, A, and mu, the measure space has characteristics of monotonicity, which means that for any measure space, the image of A is smaller or equal to the image of B if and only if A is a subset of B. Furthermore, subtractivity holds that if A is a subset of B and the image of A is strictly less than infinite, the image of the difference of B and A is equal to the image of B minus the image of A. So, the sets in our proof are infinite monotonic sequences, which means that if A1 is a subset of A2, then the image of A1 is smaller or equal to the image of A2, and so on and so on. Now to the sigma continuity property. According to Theorem 2.18, for a measure space with omega, A, and mu, if A1, A2, etc. are elements of the sigma algebra A, the sigma continuity from below for which A1 being a subset of A2, etc., due to monotonicity of the measure space. The limit of the images is equal to the image of the countable unions of the set. To illustrate this, let's assume the closed metric space An. Then we see that for A1 the interval is 0, for A2 it is from -1/2 to +1/2, etc. And the corresponding lengths of the intervals are 0 for A1, 1 for A2, etc. If we look at the limit for n, the corresponding length of the limit equals 1, and according to the sigma continuity, the image of the countable unions also equals 1. Now let us look at the proof of the sigma continuity property. The square on the right side represents omega, and the gray circle within represents the sigma algebra. Within the gray circle are blue circles, which represent the subsets of the sigma algebra. Some of the blue circles overlap, and the pairwise intersection is not the empty set. Therefore, the sigma additivity does not hold. To circumvent this, we set C1 equal to A1 and Cn equal to the difference of An and the countable union of the sets A of the sigma algebra from I equals 1 to n minus 1. By doing so, the intersection of the resulting sets are pairwisely disjoint. You can see that C2 in the blue circle has no intersection. No intersection with A1 anymore, because C2 equals the difference of A2 and A1. Now we can conclude that the image of the countable union of sets A equals the image of the countable sets of C, because in the end, they generate the same big gray circle, and if we apply a measure function on the gray circle, we will get the same results for C and A. Now we assume that the image of any subset of A is smaller than infinite for all subsets, and therefore A1 is a subset of A2, etc. And we obtain that Cn equals the difference of An and An minus 1. And due to the subtractivity of a measure space, and because we assume that our image of A is smaller than infinite, we conclude that the image of Cn equals the image of An minus the image of An minus 1. And then we get that the image of the countable unions of the set A are equal to the image of countable unions of C. Furthermore, we conclude that the countable union of the sets A in the big circle are equal to the countable union of the sets C in the big circle, because if you create the union of all the circles within the big circle to infinity, in the end they will be the big circle. The only difference is that the sets of C are not overlapping, unlike the sets of A. Due to the sigma additivity, we can express the image of the countable union of C as the image of A1 plus the infinite sum, starting by n equals 2 of the image of An minus the image of An minus 1. Therefore, we conclude that it is equal to the limit of the images of An. For the next step, we assume that the gray circle is now A1 and that every circle A2, A3, etc. is a subset of A1. Again, we want to get pairwisely disjoint sets, so we set Bn equal to the difference of A1, which is now the superset of A2, A3, etc., since they are part of A1. and an. So for n equals 1, we get the difference of a1 and a1, which is the empty set. And for n equals 2, we get the difference of a1 and a2, which is the remaining part of the gray circle if we subtract the blue part from it. Now we create a countable union of the sets A, which equals the difference of A1 and the countable union of the sets of B. To illustrate it, assume we want to get the intersection from A1, A2, and A3. Then we look at the gray circle and subtract from it the B1, which is the empty set, and then B2, which is the remaining part of the gray circle, and then B3, which is the entire circle minus the blue A3 circle. After all the subtractions, the intersection of A1, A2, and A3 is the small blue circle A3. Now we show that the image of the countable intersections of set A equals the image of A1 minus the image of the countable intersection of B. We can calculate the difference because of the subtractivity of a measure space. We get that the image of A1 minus the limit of the images of B, which we can conclude from the countable union of B because we proved this before in part 1. In the next step, we separate the limit of the image of B into the limit of the images of A1 minus the limit of the image of AN, because we define BN equals A1 without AN. Then the image of A1 minus the image of A1 cancels each other out, and only the limit of the image of AN remains.